Welcome to part 2 of chapter 7. We continue our work of energy and energy transfer. Kinetic energy, that is the energy that any moving mass possesses, known as the energy of motion, and we relate it to the work that is done by a force on an object. If you recall in part 1, we said that when an object has positive work done on it by a force, it gains energy. And the energy that it gains is kinetic energy. However, if the work done is negative, the object loses kinetic energy. And so we will formulate a relationship between one principle, that is work being done by a force, with another principle, that is energy, which an object will possess. The other form of energy that we are going to be studying is that of potential energy. We will study both gravitational and elastic potential energies. These are energies which are stored in a system whenever a force does work on the system. In other words, this is energy that might not be converted into kinetic right away, but may be stored to later at some other time be converted to kinetic energy. Let's begin by introducing kinetic energy, abbreviated by the letter K, capital K, with the units kilogram times meter squared per second squared. This combination of base units make up a unit which is known as the joule, in honor of James Watt Joule. So as we said, whenever a mass is moving, it possesses kinetic energy. How much kinetic energy is given exactly as 1/2 the value of the moving mass times its speed squared. Notice that it's a scalar quantity, and there is no direction associated because velocity squared is a scalar quantity. When we say that an object or a system undergoes a change in kinetic energy, to calculate that change, we consider its final kinetic energy and subtract its initial kinetic energy. 1/2 mv final squared minus 1/2 mv initial squared. If the difference in kinetic energy delta K is a negative number, we say that the system, or simply the object if it's a single object in the system, has lost kinetic energy, and so therefore it must have slowed down. If on the other hand delta K is a positive number, the object or the system has gained kinetic energy. It must be speeding. What happens if delta K equals 0? Well, that implies that the object has neither gained nor lost energy, and therefore the final equals initial, and so either the object's speed is constant or the object is not moving. Now, let's connect changes in kinetic energy with the total amount of work that may be done on an object. For example, here we have a mass. There is a net amount of force that is applied to the right over a displacement delta x, and we see that as a result of that net amount of force, the object sped up. It started with v initial of a magnitude represented by the length of this arrow, and it ends up with v final, a much greater speed. And we connect the idea that if we can calculate the net amount of work done on this object, it will be related to the change in kinetic energy that the object experienced. We can derive this simple relationship by remembering that work is the integral of force over minute displacement. In this case, the net amount of work and the net amount of force. Remembering Newton's second law, we can write the net force, and again we're confined to the x direction so that we only consider displacement along x, as this diagram indicates. Newton's second law, net force equals ma. We write a as the derivative of velocity v with respect to t. We rearrange the terms so that we place dx over the t and dv as now the variation in the integral. So now we have an integral of mv dv as the object moves with an initial speed v initial to a final v final. When we perform this integration, we obtain the change in kinetic energy of the object, which is merely the right-hand side of this expression. This expression is known as the work kinetic energy theorem because it links the idea of a net amount of work being done by a force with the change in the kinetic energy of the object who is the recipient of the work. Let's view an animation of work kinetic energy theorem.
How much work is done in changing an object's speed? The weight supplies a constant net force on the glider, which causes the glider to accelerate at a constant rate. The net work done in changing the mass's speed from v1 to v2 is easy to calculate. The work is 1/2 m times the quantity v2 squared minus v1 squared. The net work done to accelerate a mass from rest, v1 equals 0, to a final velocity v is 1/2 mv squared. This quantity is so important in physics that we give it a name, kinetic energy.
Okay, now let's talk about potential energy. Potential energy, represented by the capital letter U, also with the unit of joules, is stored energy. That is energy which is stored in a system or in an object. There are conditions, though, that we must consider for how this energy is stored, or when, in the case of a force doing work, when does this energy get stored? First, we say that only forces which are conservative can store potential energy in a system as they do work on it. And when a conservative force acts on a system, any kinetic energy that the system loses or gains is balanced by an equal gain or loss in potential energy. So let's state the two requirements that exist for a force to be conservative. First, it must be that the work that the force does on an object that moves between 2 points does not depend on the path that the object takes, only on where it starts, its initial position, and where it ends, its final position. Along with that is the fact that if the initial and the final position are one and the same, in other words, that the object moves in a closed path, that the force must not have done any work on the object, no net work done on it. If the force satisfies these two conditions, it's said to be conservative. If the force is conservative and does work on an object, the object is sure to store potential energy. Okay, well, let's meet our first conservative force, the force of gravity. And as such, when the force of gravity does work on an object, the object stores gravitational potential energy. But now we have to choose a reference point, a reference position about which we say the zero of potential energy exists. In this example, the floor is taken as the reference point, and a book located at a position y above the floor stores potential energy, gravitational, in the form of m, the mass of the book, g, the gravitational acceleration, times y, its height above the floor. If the potential energy of the book should change relative to, again, the reference position, then we consider its final potential energy minus its initial potential energy. For example, if the book starts at this position and rather than going to the floor, falls at some position midway, then initial y, final y, changes in the gravitational potential energy. Let's view an animation regarding gravitational potential energy.
The glider starts off with 0 kinetic energy. Because the weight can fall a distance h before it hits the floor, it has a potential energy equal to mgh. Mgh is the work required to lift a mass to a height h. When the glider is released, the force applied to the glider by the weight accelerates the glider, thereby causing it to gain kinetic energy. At the same time, the weight is also accelerating, so its kinetic energy increases as well. The weight's potential energy has applied a force to a mass over a distance. When the weight reaches the floor, it and the glider have kinetic energy, but no potential energy. In this example, energy is converted from its potential to its kinetic form.
So this is a case where we know that since the force of gravity is conservative, any losses in potential energy of the mass will result in a gain of kinetic energy of the glider. In this animation, rather than using y to represent the height above the floor, they used h. It's just a minor change in notation. How about elastic potential energy? The spring force is a conservative force. So, as long as our spring is stretched or compressed, there is a storage of potential energy, the value of which is 1/2 k times displacement squared. So in this example here, as the person compresses the spring has a stored amount of potential energy, and since it is not moving, it has no kinetic energy. But we know the instant that the hand lets go of the spring, of the block, the spring's potential energy is likely to be converted to kinetic energy. Changes in the potential energy of the spring block system, delta U, are given by 1/2 k x final squared minus 1/2 k x initial squared. Well, let's explore what happens to potential energy when work is done by an applied force. We have two examples. We have an applied force on a book that balances the gravitational force on the book, that is the weight of the book, and we also have an applied force on a spring block system that balances the spring's restoring force. In the first case, we see that the applied force, because it balances the force of gravity, in other words, it's equal but in the opposite direction, is given by mg in the positive j-hat direction. And as the book is displaced upward, its change in position will also be positive. And so when we perform the scalar product, we see that we end up with mgy final minus mgy initial. In other words, a change in potential energy, which is positive. The same is true in the case of the spring. The applied force, kx, in the i-hat direction multiplied by the displacement dx, also in the i-hat direction, yields 1/2 k x final squared minus 1/2 k x initial squared, resulting again in a positive increase of potential energy. We can view these brief animations to see how changes in the potential energy of an object subject to the force of gravity occurs. And here our mass, which is the equivalent of our book, is 1 kilogram, and we can see that as we raise it up, there is an increase in gravitational potential energy because the work done by the applied force to balance out gravity is 7.84 joules. The same is true for the spring and the block. We consider the potential energy of the spring block system as well as its kinetic energy in the case where we compress the spring or allow the spring to extend. In general, we can say that the work that is done by a conservative force, this time not the applied force, but by the conservative force, actually acts to reduce the potential energy of the system. So this relationship written out, the work done by a conservative force, is equal to the negative change in the stored potential energy of the system. If we take the integral form of work and allow it to equal the change in potential energy, the negative change in potential energy, we see that by rearranging the terms, we get an expression, FDR equals this time the derivative of potential energy, because we've taken the derivative of the integral to isolate FDR, the derivative of the change in potential energy to get du. And we see that F has the general form that it is equal to the derivative of potential energy with respect to position, R. And if we go back to the block spring system and the force of gravity, we can see that, in fact, the spring and the gravitational forces are conservative because this relationship exists. The negative du dx is equal to minus kx. And so if we want to derive an expression for the spring's potential energy, we take an integral of force times displacement and we obtain 1/2 kx squared. In the Earth particle system, a derivative of gravitational potential energy with respect to r, of course the negative of that, gives us the force of gravity. And so when we integrate both sides, we get an expression for the gravitational potential energy with the condition that now our reference energy, zero energy, will occur an infinite distance away. So that, for example, when r is equal to infinity, there is no gravitational potential energy. And we can see that this is true in this graph of 1 over r. This concludes the second part of Chapter 7. Until next time.